Welcome, the module 4 thermodynamics of solutions. In module 3, previous module, we had looked at systems comprising of a single component or a pure substance. We had developed the various useful aspects from a thermodynamics viewpoint for a pure substance, such as the PVT relationships or the equations of state in different degrees of general applicability. Then we looked at how to get the other thermodynamic variables U, S, H, A, G and so on in terms of PVT, using the reduced properties and things like that, and evaluation of fugacity coefficient also we saw. All those were for a single component. Nevertheless, this is the focus of this course is biological systems, and many systems of biological interest consists of many components. It is rare to find a system with a pure component all the time. It is quite easy to see that when you mix pure components, we get a mixture or a solution. We will look at that a little more closely. So, when the components are mixed to make this mixture or the solution, there could be changes in volume, enthalpy and so on upon mixing. What I mean by that is, you could take volume 1 and volume 2, V1 and V2. When you mix them together, the total volume may not be V1 plus V2, it could be something different from V1 plus V2. Similarly, enthalpy H1, enthalpy H2 and maybe H3, H4, depending on the number of components we are mixing together. Put them all together, the total enthalpy may not be equal to the algebraic sum of the enthalpies of individual components. Therefore, the thermodynamic properties of the mixture or the solution may not be the same as the weighted average of the relevant properties of its components. I should have said the weighted average. For example, you have the enthalpy H1 and enthalpy H2, and when you mix them together, the total enthalpy would be what fraction of component 1 you have times the enthalpy of that component, plus what fraction of the component 2 you have times the enthalpy of that component. That is not going to be equal to the total enthalpy all the time. If that is so, then it becomes an ideal solution. The ideal solution, in other words, happens if the thermodynamic properties of the solution are indeed equal to the weighted average of the relevant properties of its components. If not, we have a non-ideal solution. You notice the terms here, we have seen probably seen these many times, but notice them from a fresh angle now. There is something called an ideal solution and there is something called a non-ideal solution. We will come back to this again and again. Now, let us first consider a few aspects and concepts of relevance for multi-component systems. Please pay a little bit of attention to this. This forms the bedrock of the further development for multi-component systems or solutions. Now, let us recall that the chemical potential of the pure component, especially if it is an ideal gas, we will start with simple things. If it is an ideal gas, we can write the chemical potential of a pure component as mu equals mu naught plus RT ln P. This we have already seen way back in equation 3.1a, and for a real gas you could write mu equals mu naught plus RT ln F. The P gets replaced by a F for a real gas, and for completeness of the definition, F by P pressure, total pressure, tends to 1 as P tends to 0. This was equation 3.1b. Now let us consider a concept. This is purely a concept, it is not reality. We are extracting out something for convenience in terms of the interaction between molecules and so on and so forth. We will not get into the details here, but let us introduce a concept here, and the concept is that of perfect and imperfect gas mixtures. To repeat, perfect and imperfect gas mixtures. For a perfect mixture of a gas, the chemical potential of a component I in that mixture, it is made up of many different components, let us take one component I, it is expressed as chemical potential of I, mu I, equals some mu I naught plus RT ln Pi. Pi is the partial pressure of the component I as given here. Pi is the partial pressure of the component I, and mu I naught is a function of the temperature alone, as we had seen earlier. This is for a perfect mixture of gases. For an imperfect mixture of gases, the chemical potential of a component I in the mixture is expressed as mu I equals mu I naught plus RT ln of a certain Fi hat, fugacity of the component I in solution. That hat implies solution, the component in solution, and because the pure component fugacity may not be equal to the fugacity of that component in solution. To differentiate between that, the pure component fugacity was Fi that we had already seen earlier. The fugacity of the component I in solution is given as Fi hat, and again we should state for completeness that Fi hat by the partial pressure of I, Pi, as you know, partial pressure is the pressure exerted by that part of the gas mixture alone, which corresponds to the component I. Fi hat by Pi tends to 1 as the total pressure tends to 0. Let us call this equation 4.2. Here mu I naught is still a function of temperature alone, and let me repeat this, it will become a little clearer. Fi hat is the fugacity of the species I in the mixture or the solution, which may not be the same as the fugacity of the pure component when it exists separately. Fi hat by the partial pressure is defined as the fugacity coefficient phi I of that component. We will call that equation 4.3, and phi I is sometimes called the activity coefficient also. We will call it the fugacity coefficient in this course, sometimes called the activity coefficient. In this course we will use this term activity coefficient for something else which we will talk about later. So we will limit our terminology to fugacity coefficient, but in some books, maybe in some of your reference books given earlier, you will find this term activity coefficient. You should not get confused when you find phi I being referred to as the activity coefficient. And this is again to re-emphasize, note that for a pure component a fugacity coefficient is defined as F by total pressure, whereas for a mixture the fugacity coefficient of the component I is defined as Fi hat by partial pressure. Thus for an imperfect gas mixture, in terms of the fugacity coefficient, the chemical potential of a species I is written as mu I equals mu I naught plus RT ln phi I Pi. We have replaced our Fi hat as phi I Pi, which can further be written as mu I naught plus RT ln phi I. Partial pressure is nothing but the total pressure times the mole fraction of that component in the gas mixture, and therefore RT ln phi I, which comes from here, and Pi has been expanded to Pyi. We will call this equation 4.4. Okay. We will do this again and again because this is quite a concentrated part of the course, and it will help to repeat things to get things smoothly and clearly. Initially we saw ideal gas and non-ideal gas in terms of the chemical potential. Then we brought in the concept of perfect and imperfect gas mixtures. You put various gases together, various pure gases together, then you get a gas mixture, and we had looked at perfect and imperfect gas mixtures definition. That was again a concept. Here let us look at an ideal gas solution. An ideal gas solution is one for which the following relationship holds for every single component in the solution. Mu I equals a certain mu I hash. Okay. This mu I hash is different from mu I naught. Mu I hash plus RT ln of the mole fraction of the gas in the mixture Yi. Let us call this equation 4.5. It is a nice simple definition. It is good to remember this. Mu I equals mu I hash plus RT ln Yi. Excuse me. Here mu I hash is a function of both temperature and pressure. You will have to note this. Earlier that mu I naught was a function only of temperature. Here mu I hash is a function of both the temperature and pressure. And note, okay, this could be a little tricky now, it will become, you will get comfortable with this later. It is not necessarily equal to mu I naught plus RT ln P, okay, because if you expand this you could write mu I naught plus RT ln Pyi and so on, but note that mu I hat need not necessarily equal mu I naught plus RT ln P. Just take it on face value for now, this is the definition. Pi in equation 4.1 can be written as Pyi, where Yi is the mole fraction of component I in the solution. We have seen this earlier itself. That is, you know, you could write this definition. Yeah, mu I naught plus RT ln P, and the Pi in 4.1 could have been written like this for expanding. Yeah, that is just making a point again, I think. Now note this form, mu I equals mu I naught plus RT ln Yi, equation 4.5. This is in terms of a certain function which is a function of both temperature and pressure and the mole fraction. This is a very convenient form to write our chemical potentials in. The same form can be used to represent ideal solution of liquids and solids as well, in the mixtures of liquids and solids, homogeneous mixtures of liquids and solids, mixtures of liquids and solids. Earlier it was for the mixtures of gases alone. So for an ideal solution of liquids and solids, for every component I, mu I equals a certain mu I hash plus RT ln Xi. This is equation 4.6, which can be written as mu I naught plus RT ln Fi hat, going by a previous way of writing things. This is a more convenient thing to remember, please go by this. This is only in certain ways of representing it. If there is an interest to represent it in other ways, equals mu I naught plus RT ln Fi Xi. Fi hat has been written as Fi Xi. mu I naught we know is mu I hash, I am sorry, we know is a function of both the temperature and the pressure, and Fi is the pure component fugacity of the component I, this is known. Xi is the mole fraction of the component I. Note this form, mu I equals mu I hash plus RT ln Xi, and by with this, earlier we had mu I equals mu I hash plus RT ln Yi, and here we have mu I equals mu I hash plus RT ln Xi, and therefore we have essentially covered gases, liquids and solids. So pretty much we have a comprehensive way of representing things for all the systems that we would be interested in. Now let us bring in the non-ideal gas solution. For a non-ideal gas solution, the following relationship holds for every component I in that non-ideal gas solution. This is again gas solution. Mu I equals mu I hash plus RT ln phi I Yi. This is equation 4.7, which can be written as mu I naught plus RT ln phi I P Yi, and what I would like you to note is that for an ideal gas solution, our formulation was mu I equals mu I hash plus RT ln Yi. Here for a non-ideal gas solution, it is mu I equals mu I hash plus RT ln phi I Yi. This phi I is what brings in the non-ideality aspect. And for a non-ideal liquid or a gas solution, you could have this mu I in the same form equals mu I hash plus RT ln a certain gamma I, which brings in the non-ideality of the solution times Xi. And what did we mean by non-ideality? If you go back, we said that if you put in various components, then their the weighted average of their properties may not equal the actual property of the solution itself. So that is the non-ideality that we are talking about. So here mu I equals mu I hash plus RT ln gamma I Xi, which can also be written in terms of, well, before I say that, this needs a certain completion, or a certain part of the definition needs to be given for completion. Gamma I tends to 1 as Xi tends to 1. Note this, earlier the earlier case it was f by p tending to 1 as p tending to 0. The same vein here, but different details. Here mu I equals mu I hash plus RT ln gamma I Xi, gamma I tends to 1 as Xi tends to 1, the mole fraction tends to 1. We will call this equation 4.8, which can be written in terms of mu I naught as mu I naught plus RT ln gamma I Fi Xi. Gamma I is called the activity coefficient of the species I. This is a new concept that we are introducing in this particular module. It is called, gamma I is called the activity coefficient of the species I, and most importantly note that it is a function of temperature, pressure as well as composition. Okay, we have all three things coming in here. We need to be a little careful when we handle gamma I. Now that definition that we gave works well for many liquid solutions. The definition was mu I equals mu I hash plus RT ln gamma I Xi, and gamma I tends to 1 as Xi tends to 1. Now that works well for many liquid solutions, but not all. It poses difficulties when some of the components of the solution are either gaseous or solids at temperature and pressure of interest by themselves. In a solution they are in solution, whether a liquid solution or a solid solution and so on and so forth, but they exist in a different phase when you consider them as a pure component. Why does this become a problem? It will become very clear now. Before I say why it becomes a problem. It is very relevant here because it includes biologically relevant situations such as aqueous solutions of oxygen or glucose. When we have a bioreactor for producing various biologicals, and if the organism is aerobic in the bioreactor, we need to provide it with oxygen. The oxygen under normal conditions, standard temperature pressure or room temperature pressure, is a gas which is in the gas phase, and it needs to be dissolved in the liquid for the organisms in the broth, in the bioreactor broth, to take it up. Therefore, there we have a solution of oxygen in the water predominantly, or the broth in which the organisms are grown. In the broth, the oxygen is in the liquid phase, whereas in normal conditions at the same temperature and pressure as the broth, it is a gas phase. In other words, if the mole fraction of oxygen in the broth is hypothetically varied from 0 to 1, the phase changes, the phase of the component changes, and that is a problem. We will come to that formally in a little while. Similarly, it is glucose. Glucose is a solid at normal temperature pressure, the powder that we eat and so on and so forth, glucose. When we use it for growing microorganisms, we need to dissolve it in a liquid, and we have a liquid solution that contains glucose. And therefore, when we change the concentration of glucose hypothetically in the solution from 0 to 1 mole fraction of glucose, let us say, then it goes from being a complete liquid at mole fraction slightly more than 0 to a solid at a mole fraction of 1. So there we have some difficulty. We will see how to handle that. Again, that is what is said here. The difficulty arises because a change in phase of the solution will occur when the mole fractions of the components are varied between the two extremes of 0 and 1. But we are saved by this note, or by noting this aspect. The behavior of the components approaches ideality both when the mole fraction tends to 0 or 1. The mole fraction is 0, it is a complete solution with no component in it. When it tends to 1, it is all a pure component. Therefore, at the two extremes we approach ideal behavior, we are not in the solution regime, and therefore when we come up with a convention, we can use a suitable convention that involves this. This comes in handy with using a different convention for solutions when some of the components are gases or solids. For such solutions, a difference is made between the solvent. We write an equation for the solvent and another equation for the solute. For the solvent, we indicate it by the subscript 0 or O, and for the solute we use the subscript I. For example, the solvent chemical potential is expressed as mu 0 equals mu 0 hash plus RT ln gamma 0 x 0. You can use O also, mu O equals mu O hash plus RT ln gamma O x O, and of course this needs completion, therefore gamma O tends to 1 as x O tends to 1. Whereas for the solute we write this as mu I equals mu I hash plus RT ln gamma I x I, and gamma I tends to 1 as x I tends to 0. Now the difference is here, x O tends to 1, gamma O tends to 1, here as x I tends to 0 for the solute, gamma I tends to 1. Therefore this makes it consistent, and this is the set of definitions that are used while dealing with tricky solutions, and as usual our biological systems are full of tricky solutions, so we need to use this. we will call this equation 4.9. Where are we? Okay. Since we have covered quite a bit of intense material today, let us go through it again for completeness. This is going to become a part of you only if you look at it a few times. I am going to help you as a part of the class itself to look at it one more time. We said that we have an ideal solution. It is just reviewing in a systematic fashion what we did so far today. I think it is worthwhile doing that now. Ideal solution is the one if it happens if the thermodynamic properties of the solution are equal to the weighted average of the relevant properties of the components, which may not always be the case. When it is not equal to the weighted average, it becomes a non-ideal solution, which is the usual case. And then we said we will look at a few aspects and concepts of relevance for multi-component systems. We recalled initially the expression for chemical potential for a pure component that we wrote for an ideal gas. We said that for an ideal gas the chemical potential mu can be expressed as mu naught plus RT ln P, and when it became a real gas, when there is interaction between molecules that need to be considered and so on and so forth, then we said we could write mu equals mu naught plus RT ln F fugacity, and F by P total pressure tends to 1 as P tends to 0. So what was mu equals mu naught plus RT ln P for an ideal gas became mu equals mu naught plus RT ln F for a real gas. And we said that we will introduce a concept that we will use later, which is that of perfect and imperfect gas mixtures. Please take this on face value as of now. For a perfect gas mixture, the chemical potential of component I in the solution is expressed as, excuse me, mu I equals mu I naught plus RT ln Pi. Here you have the partial pressure, and mu I naught is a function of temperature alone. And for an imperfect mixture of gases, we had the chemical potential of component I as mu I equals mu I naught plus RT ln Fi hat. Fi hat is the fugacity of the component I in solution, which could be different from the fugacity of the pure component itself, which is given without the hat. And for completeness we will have to say that Fi hat by the partial pressure Pi tends to 1 as P tends to 0. I will be with you in a minute. The animation is not working. Okay, yep. Okay, now we are fine. So then we said that the same way that we defined the fugacity coefficient phi for a pure component, there it was just F by P, and here we have for a component and solution, excuse me, of an imperfect gas mixture, Fi hat by Pi was defined as phi I, fugacity coefficient, sometimes called the activity coefficient also, but do not confuse this with the activity coefficient that we used later. So in this course I said that we will use fugacity coefficient for phi I and activity coefficient for gamma I. For an imperfect gas mixture, in terms of fugacity coefficient, if we could write mu I equals mu I naught plus RT ln phi I Pi, which was mu I naught plus RT ln phi I P into Yi. Now we looked at ideal gas solutions. The ideal gas solutions is one for which the following relationship holds for each component, which was mu I equals mu I hash. Mu I hash is a function of both temperature and pressure plus an RT ln the mole fraction Yi in the gas phase. and also note that mu I hash need not necessarily be equal to mu I naught plus RT ln P. And what is nice about this formulation is that you could directly extend it to the ideal solutions of liquids and solids as well. I hope you are able to visualize liquid solutions, that is a little easier, but solid solutions too, where all the components of the solution are solids. Here mu I was mu I hash plus RT ln Xi. Xi is the mole fraction of the component I in that particular liquid or solid solution, which can be written as mu I naught plus RT ln Fi hash or Fi hat, which is equal to mu I naught plus RT ln Fi Xi. This is expressed Fi hat as Fi Xi, and of course mu I hash was a function of both the temperature and the pressure, and Fi is the pure component fugacity of the component I. Then for a non-ideal gas solution, we said that the following relationship holds, again the same beautiful formulation, mu I equals mu I hash plus RT ln phi I. You know, this phi I is the one that brings in the non-ideality, phi I times Yi. Yi is the mole fraction, and which could also be written as mu I naught plus RT ln phi I P into Yi. For a non-ideal liquid or a gas solution, we could write mu I equals mu I hash plus RT ln gamma I Xi. So gamma comes in for a non-ideal liquid or a gas solution, and gamma I tends to 1 as Xi, the mole fraction, tends to 1, which could also be written as mu I naught plus RT ln gamma I Fi Xi. Also I said note that gamma is a function of gamma I is a function of temperature, pressure and composition. Then we said that this definition works well for many liquid solutions, but falls apart when one of the components is either a gas or a solid, as the case with some of the biologically relevant solutions such as aqueous solutions of oxygen or glucose. We said that when the mole fraction is near 0, then of course it is a liquid solution. Mole fraction of oxygen in a solution is near 0, then it is a liquid solution. If the mole fraction of oxygen is increased to 1, it of course becomes a total gas at the conditions of interest, you know, the room temperature and so on and so forth. Similarly, glucose in solution is a liquid solution, whereas you slowly increase the mole fraction to 1, it becomes pure glucose, which is a solid. For such cases this definition will not work, essentially because there is a change of phase that occurs when the mole fraction of the components are varied between the two extremes of 0 and 1. For this we needed a different formulation, and we had used the fact that the behavior of the components approaches ideality when the mole fraction tends to either 0 or to 1. At both extremes the behavior becomes ideal as expected. 0 there is no component, 1 that is the only component, so that will be either no or a pure component. So that is an ideal situation. So for that if we represent the solvent by a subscript O and the solute by a subscript I, then for the solvent we wrote mu O equals mu O hash plus RT ln gamma O XO, and gamma O tends to 1 as XO tended to 1, and for the solute we needed to write mu I equals mu I hash plus RT ln gamma I Xi, and gamma I tends to 1 as the solute mole fraction tends to 0, and both these put together need to be used in such a situation, as we said in many biological systems, that we call as equation 4.9. Since we have seen some intense material today, let us stop here. We are also almost out of time, and when we come back tomorrow we will continue. See you in the next class.